Hello everyone, welcome back to the synthesis workshop. Today we will continue our advanced organic chemistry course, and we are joined by Phillip Grant. Phillip obtained his PhD from the University of Auckland under the supervision of Professor Margaret Burnbull and Dr. Daniel Fruckert. After that, he was awarded as a Lismetano postdoctoral fellow in Professor Nuno Moraes' lab. And now he just started his independent career as an assistant professor at Nanyang Technological University in Singapore. In our previous episode of the asymmetric catalysis module, we have been introduced to the ways of accessing inertially enriched products. This time, we will be focusing on one of the most popular reactions in asymmetric catalysis, that is the carbonyl reduction. Now I will turn it over to Phillip.
Hi everyone, thank you for joining me to take a deep dive on the topic of asymmetric catalytic carbonyl reduction. We'll be covering the major approaches to reducing ketones to form chiral alcohol products, stopping along the way to discuss their pros and cons, and to consider the mechanisms at play. So let's get stuck into it. So, as many of us will remember, ketones are commonly used electrophiles in organic synthesis. There is a range of nucleophiles that will add to a ketone, such as a Grignard reagent or an enolate, and the resulting product is an alcohol. When a ketone has two different groups attached to it, it is considered prochiral, meaning the addition of a nucleophile can occur from either the top face or the bottom face, and the resulting product is chiral. If the addition is not controlled in some way, it'll happen 50% from one face and 50% from the other face, and the resulting product will be formed as a racemic mixture, as shown here. This lecture relates to the stereo-controlled addition of H- or hydride as a nucleophile to prochiral ketones, with a special focus on catalytic systems. As shown here, the addition of H- to either the top or bottom face of a prochiral ketone will give one of two products, which will be the mirror images of each other. Note that since H- is the nucleophile here, we can refer to this reaction either as a nucleophilic addition or a reduction reaction. Both are accurate descriptors, but reduction is probably the more commonly used one. Now, we have our prochiral ketone. How can we achieve facial selectivity to give an asymmetric carbonyl reduction? We can either begin with a chiral substrate, in which the existing chirality directs addition of the hydride to one face over another. You can see an example of this here, which is called the Narasaka-Prasad reduction. This type of reaction is referred to as diastereoselective. What if we don't have a chiral element existing in our molecule already? Well, in that case, the chiral element has to come from the hydride source itself. That is to say, we would use a type of chiral hydride source to affect this reaction. Substrate control can be really useful when carefully planned into your synthetic route. But reagent control is generally considered superior because it allows for a much wider range of ketones to be used, since the only theoretical prerequisite is that R1 and R2 are different. Reagent control methods will be the focus of our lecture, but I'll make sure to include a link in the description to a resource for those who want to know more about substrate controlled methods. So, reagent controlled methods can either be catalytic or stoichiometric. As I mentioned earlier, the focus of this lecture will be on catalytic reagent-controlled methods, but I'll touch briefly on stoichiometric methods before we get stuck into that. As a quick refresher, we should remember that a catalytic reagent is only used in small amounts because it is not consumed in the reaction. In contrast, stoichiometric reagents are consumed during the reaction and are therefore needed in equal or greater molar quantities than the substrate we're using. In the context of asymmetric carbonyl reduction, there are a number of chiral stoichiometric hydride sources. Alpine borane is one such example, which is derived from 9-BBN, an achiral hydride source, and pinene, which is the source of chirality in the reaction. Together they form alpine borane, which is capable of delivering a hydride to a prochiral ketone in asymmetric fashion via a boat-like transition state. While in this case, pinene can actually be recovered from the reaction, it is generally preferable to use a catalytic amount of your chirality source in order to minimize waste. So, as part of this lecture on catalytic asymmetric carbonyl reduction, We're going to look at the CBS reduction, the Noyori reduction, and enzymatic approaches to carbonyl reduction. So let's get stuck into it. The CBS reduction is a very reliable method for ketone reduction, which uses a chiral oxazoborylidene catalyst and a stoichiometric borane as the hydrate source. It is most effective when there is a considerable size difference between the two groups of the ketone. The catalyst derives its chirality from proline, which is a chiral pool starting material. Through a few easy steps, it can be converted to the active catalyst, which provides a chiral environment both to coordinate the boron as well as the ketone substrate. The key to this ability to hold both reaction partners in a fixed orientation, thereby enabling facial selectivity, comes down to having a Lewis acidic boron atom next to a Lewis basic nitrogen atom, both positioned on a chiral scaffold. Let's take a closer look at that on the next slide. So, the first step in our catalytic cycle is to coordinate the borane to the Lewis basic nitrogen atom. This step is reversible. The effect of borane coordination is twofold: increased ability of the borane to donate a hydride atom, as well as increased Lewis acidity of the boron atom of the catalyst. This, in turn, encourages coordination of the ketone substrate to the boron atom, thereby increasing the electrophilicity of the ketone. The net effect? Both the ketone and the borane are activated and positioned in a specific orientation facilitated by the catalyst. In the traditional mechanism, this orientation allows for a boat-like transition state in which the large group of the ketone is facing away from the R group of the catalyst, thereby minimizing steric clash. The hydride is delivered to one face of the ketone by a six-membered boat-like transition state, and sterics are ultimately accountable for the selectivity. After transfer of the hydride, the release of the alcohol product turns over the catalyst, allowing the reaction to progress. The traditional model is a convenient one and easy to understand conceptually. Unfortunately, a recent study by Schreiner and co-workers have shown that sterics are actually not the decisive factor in selectivity. In fact, it is attractive London dispersion forces, not repulsive steric interactions, which underpin the selectivity. To be specific, it is London dispersion forces between one of the phenyl rings of the catalyst and the large substituent of the substrate, which lead to the stabilization of one transition state over the other. So instead of the large substituent acting to repel the catalyst, it is actually its ability to attract the catalyst which is important. Remember, the larger a molecule is, the more significant London dispersion forces are. This is the reason why decane boils at a higher boiling point than pentane. The London dispersion model is counterintuitive, but it helps us to explain some unusual cases where ketones with groups of similar sizes are reduced with good selectivity. For example, this parafunctionalized benzophenone derivative, the two groups are nearly identical in size, but the electron-rich paramethoxyarene forms stronger London dispersion interactions with the catalyst. But let's not get bogged down with unusual examples. Let's finish with a classic example showing just how useful the CBS reduction can be. For example, this ketone, where the phenyl group is considered the large group, was reduced in 96% EE to set up a key stereocenter in the synthesis of fluoxetine, otherwise known as Prozac. Another important approach to catalytic carbonyl reduction is the Noyori hydrogenation. In the Noyori hydrogenation, a ruthenium catalyst bearing a chiral ligand is used to activate gaseous hydrogen for its addition across the carbon-oxygen double bond of a ketone. It has been shown to have the benefit of low catalyst loading, which is important when using a precious metal, and it's been shown to work well on large scale. For this discovery, Noyori won the 2001 Nobel Prize in Chemistry alongside Knowles and Sharpless. So let's take a closer look at its mechanism. Now the mechanism can look a bit complicated at first, but let's take it step by step and pick out the key points. The catalyst is thought to originally be present in a polymeric form, which is depolymerized to its active form by coordination of the solvent, in this case methanol. Following this, activation of hydrogen occurs, which produces a small amount of hydrochloric acid, when the chloride anion is present. But most importantly, it forms a ruthenium hydride species, which unlike elemental hydrogen, is reactive towards our ketone substrate. Coordination of the substrate normally displaces two solvent ligands. One is displaced by the lone pair of the ketone oxygen, and another is displaced by a heteroatom anchor point of the substrate. This is important for holding the ketone in place, and we'll discuss it in more detail soon. Now that the ketone is coordinated to the ruthenium center, it is important to remember that the chiral diphosphine ligand means that of the two possible orientations for substrate binding, one will be lower in energy due to less steric clash with the chiral ligand. This is another important point which we'll go into more detail with soon. Now for the magic, transfer of a hydride species to the carbonyl carbon. This happens in a stereoselective manner, giving the chiral product shown here. After release of the product, the catalyst can be recycled by activation of another molecule of hydrogen. Now that might seem like a lot of information, but don't worry, we'll go through each of these aspects carefully in the slides that follow. Now some of you might be asking the question, might this reaction actually proceed by a hydrogenation of the enol tautomer of the beta-keto ester, or alternatively, conjugate addition of a hydride to the enol tautomer? Well, early mechanistic studies probed this possibility with two experiments. The first involved an alpha-dimethyl substrate which proceeded with high yield and enantioselectivity without the possibility of proceeding via an enol tautomer. Further evidence for hydrogenation occurring via the enol tautomer was obtained by the hydrogenation of a deuterated substrate. If hydrogenation proceeded by the enol tautomer, the product should have no deuterium at the alpha position, because it would have been transferred to the oxygen atom and eventually lost by exchange with the solvent. However, the alpha deuterated hydroxy ester was obtained, again suggesting that the relevant species is the ketone rather than the enol tautomer in the reduction reaction. You may notice that this reaction has been stopped at just 1.3% conversion. I won't get into the exact reasons for this because it's a rather complicated story, but if you're interested to find out more, I would encourage you to dig into the reference at the bottom of this slide. Or even better, why not start a discussion in the comments section below? Now let's get stuck into the stereoselectivity of the process. To recap, the stereoselectivity of the Noyori hydrogenation comes from the axial chirality of the binap ligand. It is difficult to imagine the chiral environment around the metal center just by looking at the catalyst drawn in two dimensions. Imagine instead that we are viewing the catalyst from within the plane of the page, much like the way a substrate would, quote-unquote, see it. From this angle, we can divide the four corners of the catalysts into two open quadrants and two closed quadrants. The closed quadrants are the ones that are already filled with a phenyl ring protruding from the phosphorus atom, whereas the open quarters, or quadrants, are unoccupied because the phenyl ring is pointing away from the metal center. If we are a substrate, we want to fit into the open quadrants, where steric clash is minimized. Let's look at that closely. In the left orientation, the carbonyl group and its methyl substituent do not clash with this phenyl ring. However, the orientation on the right, which would give the opposite enantiomer, there is a significant clash with the phenyl ring. Hydrogenation would thus proceed to the face of the carbonyl shown on the left side rather than on the right side. So far we have focused on beta-keto ester substrates for Noyori hydrogenation. Let's take a look at what other substrates can be used. There are two main requirements for the substrate to undergo Noyori hydrogenation with high stereoselectivity. The first is a heteroatom, shown here as X, and the second is an appropriate length tether separating that heteroatom from the carbonyl group. This should generally be around 1 to 3 atoms. The heteroatom is there to allow the substrate to coordinate to the metal center via a second coordination site, holding that substrate in a fixed position while hydride transfer occurs. If the substrate were able to freely rotate, there would be a greater likelihood of mixed hydrogenation from both faces. The length of the tether also influences how well the substrate binds to the catalyst in a bidentate fashion. If the tether is too large, then bidentate coordination may become unfavorable. As you can see by this table of substrate, a diverse range of compounds can be synthesized provided that these two requirements are met. Another aspect that makes the Noyori hydrogenation so powerful is its application to kinetic resolution. Take for instance the hydrogenation of this racemic alpha-hydroxy ketone. When the reaction is halted around 50%, the enantiomer syn diol can be obtained, leaving behind an enantiomer-enriched alpha-hydroxy ketone. This is due to the fact that one enantiomer of the starting material reacts faster than the other, in this case by a factor of 64. While this is a useful reaction, it is limited to a theoretical maximum yield of 50%. Ideally, we would be able to use all of the starting material and not just half of it. A step up from the standard kinetic resolution is the dynamic kinetic resolution. In this type of resolution, all of the starting material can be converted to the product. This is by interconversion of the two starting material enantiomers. Take for example the hydrogenation of this beta-ketoester. Both enantiomers of the beta-ketoester are present in solution because they rapidly interconvert by keto-enol tautomerization. The R enantiomer of the binap-ruthenium catalyst reacts faster with the S enantiomer of the starting material, and when it does react, it prefers to give the syn product. The end result of this is that the diastereomer shown here is preferentially formed over the other four. For this process to be efficient, there are a few key requirements. Firstly, stereochemical inversion of the substrate should be faster than hydrogenation, to avoid the unreactive isomer becoming the main species in solution, which would detract from the overall stereoselectivity. Secondly, the catalyst must react faster with one substrate than the other. This is the same as with the regular kinetic resolution. And lastly, hydrogenation of the favored substrate should be highly diastereoselectivity. That is to say, the syn product, in this case, should be formed much faster than the antiproduct from the S isomer of the starting material. These three facets allow for selective formation of one diastereomer out of a possible 4 with a theoretical yield of 100%. Let's take a quick look at an example. This alpha amino ester can be converted with high stereoselectivity to this diastereomer, leaving behind only a small portion of the antidiastereomer. In both cases, the catalyst directs the hydride to the back face, resulting in the alcohol coming out of the page. The stereochemistry at the alpha position is in part determined by the substrate itself. If we take a closer look at the stereochemical model, we can see that a hydrogen bond between the ester and the NH of the amide helps to favor formation of the syn isomer. In a simpler example, bearing only a methyl group, both epimers are formed in roughly 1:1 ratio. This indicates that the transition states for formation of the anti and syn diastereomers are similar in energy. Now let's move on to the growing field of biocatalytic ketone reduction, our last stop for today. Biocatalysis is another important approach to carbonyl reduction, which offers a few key advantages. The reactions are generally mild, can be scaled up for industrial applications, and are generally greener than traditional methods. In recent years, the utility of biocatalysis has grown considerably as methods for protein engineering have become more sophisticated. One important family of enzymes when it comes to ketone reduction is the ketoreductases. These enzymes, when performing their native function, serve to transfer a hydride from a sacrificial donor to the substrate. They do this by first transferring the hydride, in this case from glucose 9-phosphate, to the cofactor NADP+. NADP+ is converted to its reduced form, NADPH, which serves as a hydride donor, transferring the hydride to the ketone substrate. Due to the chiral environment created by the enzyme active site, transfer of the hydride often occurs with a high degree of stereoselectivity. On the next slide, we'll discuss an example where ketoreductase was used in the synthesis of a pharmaceutical. Montelukast is an asthma and allergy treatment with the structure shown here. A key step in the original industrial process was a dip chloride reduction, which required a stoichiometric amount of the chiral reagent. Not only was a stoichiometric amount required, but dip chloride is corrosive and moisture sensitive, which makes it a nasty reagent to use on large scale. Remember what we discussed earlier in the lecture, a catalytic method would be better. But unfortunately, the CBS and Noyori reductions failed with this substrate, which was because the styrene moiety shown here was sensitive to hydrogenation. Let's see how biocatalysis was able to step in and save the day. The authors began their study by screening a number of commercially available enzymes to find one that exhibited some promising activity. They found one commercial keto reductase enzyme was able to give the desired alcohol with high enantioselectivity, making use of cheap and innocuous isopropanol as the hydride source. However, this enzyme was only efficient at low concentrations of substrate and required a large amount of catalyst loading. Still, it provided a great starting point for the development of a better enzyme using directed evolution. For those who aren't familiar with the topic of directed evolution, have a read of the resources that are provided at the bottom of the slide. Unfortunately, it is too big of a topic for this lecture. But in short, directed evolution mimics natural selection, producing mutants of a given protein, then selecting for those which exhibit an improved function in some way. In our case, this involves random changes to the amino acid sequence of our K-red enzyme, ultimately leading to one with improved activity for our desired reduction. So, after 3 rounds of directed evolution, a new enzyme with superior activity and stability was discovered. This enzyme could be used at up to 100 grams per liter substrate concentration in a mixture of toluene, isopropanol, and aqueous buffer solution. The catalyst required a loading of just 3 to 5 weight% to achieve an enantioselectivity of greater than 99% based on the crude material. The yields were slightly improved compared to the dip chloride reduction, and the product mass intensity was reduced from 52 to 34. Product mass intensity, for those who aren't familiar with the term, is a measure of greenness of a process. It is defined as the ratio of the mass of the obtained product to the total mass of the reactants. All in all, the corrosive, moisture-sensitive, poorly atom-economic dip chloride reduction was replaced by a much greener biocatalytic reduction through the power of directed evolution. And that brings us to the end of our lecture. To recap some key take-home messages. Ketones are valuable prochiral molecules where R1 and R2 are different. We've looked at asymmetric reduction, but the addition of a variety of nucleophiles will also give chiral products. Secondly, catalysis has massive advantages over stoichiometric reduction methods, principally because only a small amount of the chirality source is needed. And lastly, asymmetric reduction is a means to synthesize important medicines. It may not seem like it, but ketone reduction plays a part in fighting disease. We should not forget how advances in organic chemistry have a real-world impact in this way. So that's all from me. Thank you for joining, and thanks to Matthew for having me on the synthesis workshop. Bye for now.
Thanks, Phillip, for the nice talk. Asymmetric carbonyl reduction can provide chiral alcohol moieties that ubiquitously exist in natural products and medicinal molecules. The 3 strategies, combined with their application in the synthesis of APIs, introduced by Phillip today, provide us with a nice overview within this area. As he said, leave your comments if you have any questions. Thank you for joining. We will see you next time.